let's do the usual thing, mic check and all that. Oh, and I need to mute that. Good thing I remembered. Come to think of it, okay, yeah, that microphone is also muted. That's good. Let's check the status of the stream, and do I hear myself? Yes, I do. Okay, perfect. And do I see my hand? Yes, I do. All right, everything looks good. Let's get back to it. So, a couple minutes late, as per usual. I thought I'd be starting like 5 to 10 minutes early, but life likes to throw curveballs at me. Amazing how that rarely happens with the gaming streams, though. Anyway, let me see what was on the agenda for today. I wanted to start things off by resuming a problem that I abandoned last time because I wasn't sure how to proceed with it. And that was problem 37 from my book, in case you weren't here for last week. The book I'm using right now is the free digital book that you can get from OpenStax, OPENSTAX. I think the website is openstax.org, but just type the word OpenStax into Google and you'll find it. They've got free textbooks for a variety of subjects that you can download, and I'm using their Calculus Volume 3 book, although I have a downloaded copy from a few years ago, so if you're using the latest version, there might be some discrepancies. I don't know if it has been updated since I last downloaded it. So if you see any discrepancies, that's the reason. Anyway, page 118 of that book, in case you wanted to follow along, assuming the paging is still the same, I have problem 37, which says, let vector A be the vector with components A1 and A2, similar story for vector B, and vector C, similar story, and let them be three non-zero vectors. If A1b2 minus A2b1 does not equal 0, then show that there are two scalars, alpha and beta, such that C is equal to alpha A plus beta B. So what they're trying to tell you here, this A1b2 minus A2b1, I worked it out last time, and I showed that if it was 0, then that would mean that vectors A and B would be parallel to each other, which would mean that they're just multiples of each other, which doesn't really give you a lot of leeway. If you try to make vector C as a combination of some multiple of A plus some multiple of B, where was it? Right here. If you want C to be some multiple of A plus some multiple of B, then if A and B are parallel to each other, if this difference is equal to 0, then there'd be no point. C would just be, you could represent it entirely as just a multiple of A or just a multiple of B if A and B were already multiples of each other. But if A and B are not parallel, if A1b2 minus A2b1 does not equal 0, then you can make any vector C from some combination of vectors A and B, mixed in different amounts, adjusted by these alpha and beta values. So last time I kind of got stuck and wasn't sure what they wanted me to do, but over the week I was able to give it some more thought and realized that I was missing something important, which is we can treat vectors A, B, and C as givens. We can treat A, B, and C as givens. So what the problem is really asking us is, given A, B, and C, show that you can come up with an alpha and a beta for any C that make this equation true. For any C, you can find an alpha and a beta such that you can make any vector C out of some combination of A and B. This is what we call a linear combination, by the way, when you take a multiple of one thing plus a multiple of another thing. That other multiple can be the same but doesn't necessarily have to be, and usually isn't. If you take one number times one thing plus another number times another thing, then you have combined those two things. You have created a linear combination of those two things, and of course you can make linear combinations of three things or four things and so on and so forth. So for example, I could do, instead of Greek letters, I'll just use, how about S, T, U, and V for my coefficients. Let's say I wanted to make some sort of linear combination of SA plus TB plus UC plus VD. This is also considered a linear combination of four vectors, and the things that you're linearly combining don't even have to be vectors. You can make linear combinations of scalar quantities as well. What makes it a linear combination, where the term linear comes from, is the fact that your variables, in this case the vectors, are to the first power. So yeah, that term linear combination, you'll come across it if you end up doing linear algebra after you finish your multivariable calculus course. And not that you have to do multivariable calculus first. You could take linear algebra first. You could even take it before any form of calculus, although you might be a little bit restricted in some applications. But usually linear algebra is taught after students have completed all of their calculus, because you just gain enough math experience from doing calculus that allows you to digest the concepts in linear algebra a little bit more comfortably. Oh, and I just realized I don't need these headphones on my head. Let me put them away. I knew something felt weird. Okay, where was I? So, yeah. Let me try and illustrate visually. The idea that if you have two vectors that are not zero and are also not parallel to each other, then you can make any other vector out of them, whether it's in 2 dimensions or 3. So visually, I can illustrate it like this. Let's suppose I have one vector that, for the sake of simplicity, we'll say it points to the right. Let's call this vector x. You know what? No, I'll call it a, because x implies something that I don't want to imply. And let's say we have another vector, and let's call it vector b, and let's say it has a different size as well. So something like this. With these two vectors, I can go as far as I want in any direction. If I make linear combinations of these vectors, I can achieve literally anything. I can get any vector in any direction I want. All I have to do is choose the appropriate scalars. For example, if I wanted to go left, I could either take a negative scalar multiplied by a, or I could take a negative scalar multiplied by b. If you go the b route, then you're also moving in the vertical dimension as well, so that's something you have to take into account. And what if I wanted to move vertically? Do I have to? Well, b is the only vector I have here that has a vertical component. So do I have to always move either to the right or to the left if I want to move up or down respectively? No, not necessarily. You could do something like, say, take a and multiply it by whatever number you need in order to make it this length. So let's call it constant k times a. Let's suppose that k times a is equal to this. And if you subtract k times a from b, then you're left with, which color do I want? Let's use purple or lavender, whatever you want to call it. You're left with this vector, which is b minus ka, and that vector points straight up. And now I can multiply this by whatever number I want in order to go up or down as many steps as I want. And there we have it. So if I wanted to go, let's say, 3 steps in the a direction, which is to the right, and I wanted to go 4 steps down, then I would do 3a. That's 3 to the right. And then if I want to go 4 steps down, I could do minus 4 times, well, this is an upward step, so the minus has already taken care of that. And this was b minus ka, whatever k happens to be. And yeah, the 3 and the 4 are numbers that you can adjust so that you can precisely control exactly the magnitude of each of those components and the direction, depending on whether you add on a negative or not. So hopefully that illustrates the idea. That's what they're trying to get at with this problem. They're trying to get at the fact that if you have a pair of non-parallel vectors in 2D space, you can make any vector out of them. Similar reasoning applies to vectors in 3D, although there is a requirement in 3D where, how do I say this? Well, actually, let me think about this for a second. In 2D, if 2 vectors are non-parallel, then if one of them has no component in either the horizontal or the vertical, then the other one has to. But is that still true in 3 dimensions? Because in 3 dimensions, if I had, for example, a vector of, let's say, components 1, 2, and 0, and I had another vector of components, let's say 3, -5, and 0, then with these 2 vectors alone, it would be impossible to create any component along the z direction, which is not good. So yeah, we need an additional restriction when we go to the 3-dimensional case, but as long as at least one of the 2 vectors has a non-zero component in each of the dimensions that the vector can have components for, then you should be able to make any vector you want in that space from a linear combination of just two non-parallel vectors. But we'll explore the three-dimensional case later, maybe, if they throw a question at us similar to this one, which I have a feeling they will. Anyway, let's get to work on proving that if A1, A2, B1, B2, C1, and C2 are all known, then you can derive a formula that provides you with whatever alpha and beta you need. So if I want to do, well, I wrote those equations over there, so I'm going to copy them over to this next sheet. C1 equals alpha A1 plus beta B1, and C2 equals alpha A2 plus beta B2. So we need to prove that there is always an alpha and a beta that we can come up with that will make these equations true. Okay, that just means we have to come up with a formula for alpha and beta that depends on the values A1, B1, and C1, and A2, B2, and C2. So let's get started. We're just solving a system of linear equations, two unknowns, the two unknowns being alpha and beta. That's the part that I was missing last time. Once you realize that they want you to treat the A's, B's, and C's as knowns, the problem unravels pretty easily. So what I want to do is I'm going to do elimination. So I'm going to take the first equation and multiply it all by, what do I want to multiply by? Well, what do I want to eliminate first? I guess I will eliminate the alpha terms first. So I want to multiply this by A2 and multiply this by A1. And if I do that, then I'm left with C1A2 equals alpha A1A2 plus beta B1A2. For the second one, I'm going to have C2A1 equals alpha A2A1 plus beta B2A1. And if I take the top minus the bottom, or the bottom minus the top, it doesn't really matter, then alpha A1 A2 minus alpha A2 A1, that's just going to be 0. Plus beta, I'll have factored out, so beta B1 A2 plus beta B2 A1, I'm just going to have that as B1 A2 minus B2 A1, and that's equal to C1 A2 minus C2 A1, and solving for beta, all I have to do is divide. So I get beta equals C1 A2 minus C2 A1 over, I guess I'll write it as A2 B1 minus A1 B2. And the reason I want to write it like that is because I think, that's how it was written over here. So A2 B1 minus A1 B2 does not equal 0. This is still true if you reverse the order of subtraction. If a1b2 minus a2b1 isn't 0, then a2b1 minus a1b2 is also not 0. And that's good. That means we don't have to worry about dividing by 0. We don't run into that problem, which I guess is another reason why why this condition has to also be true, is because otherwise it would create a division by 0 situation. Okay, so that's beta. Now what we could do is plug this whole entire mess back in to the original equations and solve for alpha that way, but no thanks. So instead what I'm going to do is just basically the same process that I did. Instead of eliminating alpha, this time I'm going to try and eliminate beta. So I'm going to multiply by b2 for the top equation and by b1 for the bottom equation, and that will give me c1b2 equals alpha a1b2 plus beta b1b2, and then c2b1 equals alpha a2b1 plus beta b2b1. Top minus bottom again. Beta b1 b2 minus beta b2 b1 is just going to be 0. And I'm left with, I guess I'll factor it out. I should have made more space for this, come to think of it. Alright, c1b2 minus c2b1 like that for now equals, factor out the alpha, and we've got a1b2 minus a2b1. a1b2 minus a2b1. Okay, and I guess I'll have to move my plus sign a little bit there. Okay, and if I just divide by a1b2 minus a2b1, then I'm left with c1b2 minus c2b1 over a1 b2 minus a2 b1 equals the alpha. And there we go. Now, you might feel overwhelmed by this, you might find it unconvincing, and here's just a general math study tip. When you see stuff like this, you're not alone in finding this to be really overwhelming and hard to keep track of. There's a limit to how many variables you can keep track of in your mind. Psychologists have proven it. I think it's 7 plus or minus 2 variables that you can keep track of in your head at any given time. So what I like to do when I look at these theorems and proofs and stuff in math textbooks is I just play around with it. I assign some actual numbers and see how it works out. So let's do that. Let's say, for example, I want to make the vector, how about I want to make the vector -6, comma, oh, I don't know, how about 10? Let's say this is the vector I want to make. This is our vector C. And let's say I want to make this vector out of the given vectors a and b. The only condition for a and b is that they can't be parallel to each other. a2b1 minus a1b2 cannot be 0, which, as I showed last time, means that they can't be just a constant multiple of each other. So, for example, if I choose for a to be, let's say 2 comma 5, does 2 comma 5 work? Yeah, 2 comma 5 should be fine. If I let a be 2 comma 5, then I can't have b being like negative 2 comma negative 5. I can't have it being like 4 comma 10. I can't have 6 comma 15 and so on. I can't have that. B has to be different. B has to be such that the ratio of its components isn't the same as the ratio of A's components. So I want something different from a 2 to 5 ratio between the components of B. And one easy way to fix that is to make one of them match the sign while the other one doesn't, or you could make one of them 0 while the other one isn't. Or you could make one of the components the same while making the other one different. So there are a lot of easy options if you're just trying to create random vectors to later combine to create whatever vector is demanded of you. So I guess I'll just go with, how about 3 comma 8? How about 3 comma 8? Okay, so can I make negative 6 comma 10 out of these? The answer is of course, but let's actually watch it play out. So according to the formulas we derived, negative 6 comma 10 should be equal to alpha times 2 comma 5 plus beta times 3 comma 8. So what is alpha in this case? Alpha is going to be, let's see, C1, B2, so negative 6 times B2, that would be 8, minus C2, B1, so 10 times 3, over A1, B2 minus A2, B1. A1, B2, so that's 2 times 8, minus A2, B1, 5 times 3. 2 times 8 minus 5 times 3. This might look familiar to some of you if you did matrix math in your pre-calculus course. 2 times 8 minus 5 times 3. You might remember this as the determinant of a 2 by 2 matrix. You might remember this as the determinant of a 2 by 2 matrix. These ideas are not unrelated. Linear algebra is all about working with matrices, so get comfortable. Determinant of 2, 5, 3, 8. 2 times 8. 2 times 8 minus 5 times 3. This should give you a little bit of insight into where the formula for a determinant even comes from. The more you know. Anyway, let me draw a line here just to separate those from each other, and let's see what I get. I'm going to get some really ugly fractions. I can feel it because I just chose the numbers randomly. It's not going to come out nice. I will be shocked if this comes out to be a nice round number. So negative 6 times 8, that's negative 48, minus 10 times 3. So negative 48 minus 30, that's negative 78. And then 2 times 8 is 16, minus 5 times 3 is 15. Oh! Well, well, well. How about that? I did not plan that. The denominator is 1. I'll take it. I was expecting a really ugly fraction, but I guess we've been spared. Okay, so that's for alpha. For beta, we need to follow this formula, and I have nowhere to write this. Well, I guess I could write it over here. Let's see. For beta, so C1A2, so negative 6 times A2 is going to be the second component of A, which is 5, minus C2A1, C2 being 10, times A1 is 2. All over A2B1 minus A1B2 is A1B2 minus A2B1 in reverse, so that's just going to be negative 1. It's going to be 5 times 3 minus 2 times 8 instead of the opposite, so yeah, 15 minus 16 instead of 16 minus 5. If you reverse the order of subtraction, then you just get the negative of what you got before. Okay, negative 6 times 5, that's negative 30, minus 10 times 2, negative 30, wait, oh, right, and it's over negative 1. I was about to say, if this came out negative, that wouldn't work. Anyway, negative 30 minus 20, so that's negative 50 over negative 1 is equal to positive 50. Okay, so beta is equal to positive 50 while alpha is equal to negative 78. So let's test it out. Negative 6 comma 10 is equal to negative 78 copies of 2 comma 5 plus 50 copies of 3 comma 8. Let's test that out and see if it works. Negative 78 times 2 is, let's see, negative 80 times 2 would be negative 160. So add back 4, and that's negative 156. Negative 156 plus 50 times 3 is 150. Negative 156 plus 150 is indeed negative 6, so that works. And then for the 10, negative 78 times 5 plus 50 times 8. Oh boy, again, I'll do negative 80 times 5. That would be negative 400. Add back 2 times 5, so add back 10. And that will be 300, negative 390. Negative 390 plus 50 times 8 is 400. 400 plus negative 390 is indeed 10. All right, it works. The numbers are pretty big. Usually they give you problems where these alpha and beta values turn out to be, single digits, but just goes to show that it's possible if you're willing to go to some somewhat ridiculous lengths. You can make any two-dimensional vector out of these two. And they're not the only options. We could have chosen any pair A and B as long as they fulfilled the condition that A1b2 minus A2b1, or the reverse if you will, is non-zero. As long as those two vectors were not parallel, they would have been a pair of vectors you could combine in order to make any other vector in 2D space. In 3D, we have additional restrictions that we're going to have to look at, and I have a feeling they're going to have a problem that makes us do just that. And that one is going to take up a lot of our time. Okay, and I think that is it for that section of the book. So I want to move on to vectors in 3 dimensions. Let's have a look. So actually we did a little bit of it last time. We just did one problem, which was this problem over here. So we did get a little taste of vectors in 3D, and we established that the magnitude of a 3D vector works just like the magnitude of a 2D vector. You take the square of each component, you add them up, you take the square root. The Pythagorean theorem still works in 3 dimensions. You just have 3 things to add up instead of 2. Which is nice. We will find that a lot of things translate very directly from 2D to 3D. There will be some things you can do in 3D that you can't do in 2D, obviously, but hopefully you find it reassuring that a lot of the logic that works in 2D still works in 3D and beyond. So let's look around for some problems and see what we can learn about 3-dimensional vectors. We'll probably start with some simple ones that won't be too different from what we did in the beginning with 2D vectors last week. Let's see. 62, find the coordinates of point P and determine its distance to the origin. That's basically the same as the problem we did last time with the one that I just showed a minute ago with the rectangular prism-like setup. So I will skip on that. For the following exercises, describe and graph the set of points that satisfies the given equation. Describe and graph the set of points that satisfies the given equation. So we have one of them says y minus 5 times z minus 6 is equal to 0. Another one says z minus 2 times z minus 5 equals 0. Okay, so I guess they're just having you practice basic graphing in 3D space. I guess we can give it a go. I might need a refresher on this myself. I mean, the second one looks easy enough. You just foil it. Yeah, the second one looks like the easier of the two. It says z minus 2 times z minus 5 equals 0. Oh, wait. They're just a set of points. Okay, z minus 2 times z minus 5 equals 0. That implies then that z is equal to 2 or z is equal to 5, which you might think is just a single point in space, but you would be wrong. Let me illustrate. For example, in 2D space, what does the graph of x equals 3 look like? What does the graph of x equals 3 look like? Here's x, here's y, And here's 1, 2, 3. Here's x equals 3. Is it just a point on the x-axis? No, x equals 3 is all points in 2D space where x is equal to 3. This whole line, which extends forever, is the x equals 3 line. So now if we look in a 3D space, what are the implications? Let me draw a coordinate system. So that's going to be my x, that's going to be my z, and that's going to be my y. So there's x, there's y, and there's my z-axis. I should probably have drawn it a little lower, but I'll draw a little squiggly line to separate those from each other. And let's see, so we're looking at z equals 2 and z equals 5. Z equals 2, let's say 1, 2, 3, 4, 5, like that. And let me actually use different colors here. Okay, all points where z equals 2 and all points where z equals 5. That means you have complete free reign in x and y. X and y can be anything as long as z is 2 or 5. Those are planes. Those are entire planes, which I'm not sure I'm going to be able to draw really well, but I'll try. So let that be a plane that cuts through there and is parallel to the xy plane. And I'll try to draw something similar over here. Let me try a different color so that I don't get these mixed up with each other. I messed that up really badly. Okay, that's a little bit better. See, this is why one of my plans for this summer is to work on some 3D modeling, because a course like this could use it, and later on it'll become a lot more helpful. I mean, for later on I'm not too worried for calculus in particular, because I do have a free online 3D graphing tool that we'll be able to make good use of. So I'm not as worried about 3D modeling for calculus, but for physics, oh boy, especially for electricity and magnetism, I'm becoming increasingly convinced that teaching that course without good 3D visuals is not the way to go. Anyway, hopefully this illustration is good enough. Unfortunately, I can't do what they do in textbooks, which is do all kinds of fancy like shading that helps make these planes look better, helps guide your eyes to have the right perspective. But hopefully you can, with this, hopefully you can see what I'm trying to show you, if I haven't shown it clearly enough, which I doubt I have. Okay, y minus 5 times z minus 6, if we go back to the other one, is equal to 0. So that's going to be a similar business. That might actually be easier to illustrate. So y minus 5 times z minus 6 is equal to 0. that would imply that either y equals 5 or z equals 6. All points where y is equal to 5, or all points where z is equal to 6, or both. This is going to be the intersection of two planes, and the intersection of two planes forms another familiar shape, a line. So let me try and... I made too much space for x and y and not enough for z again. That's not good. I need to get better at planning for z. Oh well. There's x, there's y, which I've made way too big for z. And 1, 2, 3, 4, 5, 6. Okay, so z equals 6 is going to be one of the planes that I draw. Something like that. That's going to be your z equals 6 plane. And then your y equals 5 plane is going to be 1, 2, 3, 4, 5. Let's do that one in gray. How am I even going to draw this? So parallel to x and z. I want to draw something like that. And then that. Yeah, that should be good. Okay, and then the place where the two planes intersect, I want to draw that as well if I can. I have to be really careful here because this is going to be really easy to screw up. Let's see. Okay, so somewhere... there, and then parallel to the x-axis. Okay, I think I've got the right angle. Yeah. Okay, I messed it up a little bit. But yeah, something like that. They intersect in a line, and of course, these planes and this line, I guess I should put arrowheads on the line at least to show that it just spans infinite space. Same thing for the planes. I guess I could draw arrows on their corners to show that they just go on forever. I'm not going to do that every time, but just this once. And I guess there, yeah. I can see how this becomes very unhelpful when your picture is crowded. Okay. Next one is y minus 1 squared plus z minus 1 squared is equal to 1. Ooh, what's that? In 2D space, that would be the equation of a circle. In 2D space, that would be the equation of a circle. So what do you suppose it would be in 3D space? If you said a cylinder, I think you are right. So y minus 1 squared, plus z minus 1 squared equals 1. Let me try and make enough space for the z this time. There we go, z, x, and y. And here I thought I'd be doing vector stuff. I mean, we'll probably end up doing that later. Okay, so y minus 1 squared plus z minus 1 squared is equal to 1. If you just look at the y and z axes alone, you're just looking at the yz plane. This is effectively the same as looking at the xy plane. So this, if you remember your stuff from pre-calculus, is the equation of a circle at center 1, 1 with radius 1. So if I just go to, I guess I'll use a bigger scale here. So I'll say that this is 1, which makes this maybe a little higher. That is 1, so there's 1, 1, and then the radius of the circle is 1. So in the YZ plane we see a circle, but what about X? X can be anything, so this is actually an infinite stack of circles that goes, let's see, I want to try and, make them parallel to the x-axis as best as I can. Should be something like that, and I guess I'll draw that as well, just kind of going like that, and the only reason I'm struggling with this is because I'm trying to not draw the most arbitrary infinite cylinder. Otherwise, I have plenty of experience drawing infinite cylinders from electromagnetism. Okay, I think that line is a bit bent, but hopefully this is good enough to illustrate the idea. Yeah, you get a cylinder that just extends infinitely parallel to the x-axis. Okay, and we might as well look at the fourth one. It says x minus 2 squared plus z minus 5 squared equals 4. Okay, that's a circle of radius 2. And then when it extends parallel to the y-axis, you'll get another cylinder. I guess we can skip that. Okay. Next, it's asking us write the equation of the plane passing through point 1, 1, 1 that is parallel to the xy plane. I guess I'll work on that in this little space here. So passes through one and is parallel to the xy plane. Parallel to xy plane. Okay, so this would mean if it's parallel to the xy plane, then that means that it has a constant z. That would mean that it has a constant z. If you want to see an illustration of that, just look at the first of these graphing problems we did for 3D space. If you have a constant z, then you have a graph of a plane that is parallel to the xy plane. Parallel to xy means constant z, parallel to yz means constant x, and parallel to xz means a constant y. So z equals constant is the equation. And what is that constant? Well, if it passes through 1, 1, 1, then z needs to be 1. So the only way this would work is if the plane in question is the z equals 1 graph. Okay, that one wasn't too bad. Next one, write the equation of the plane passing through point 1, -3, 2, that is parallel to the xz plane. I think you can see how that one would play out. 1, -3, 2, parallel to xz. So that's going to be y equals -3. It's going to work out pretty much the same way as this one. Find an equation of the plane passing through points 1, -3, -2, 0, 3, -2, and 1, 0, -2. So what you see in common between all three of those is z being -2. We will see later equations of more complicated planes, but here they're only giving us planes that are parallel to one of your standard planes, xy, xz, or yz. So they're giving us the really easy ones for now, but we will look at more complicated planes that are like, start with these and then just tilt them at an angle and you'll get something that's kind of messy. A good way to start with drawing those planes, by the way, is to find their intercepts, if they have intercepts with all axes. Find where their intercepts are and then draw some sort of, I guess, triangle that's supposed to exist within that plane, and then from there start extending it. And drawing this by hand is not the easiest of tasks, but hopefully that gives you some idea of the underlying logic of just how to at least visualize it in your head. I find that it's easier for me to kind of just see the picture in my head of what the graph is supposed to look like in 3D versus actually trying to draw it. Drawing it is a nightmare because, again, I don't really have the ability to do like the shading and stuff that they do in textbooks. That's what I've realized lately when trying to figure out why is it that no matter how hard I try, I can't seem to get graphs that resemble what I see in my textbooks. For the longest time I thought, well, they just draw the 3D shape in a single color, why does it matter? Why does it work so well? Whereas when I try to draw the same thing, it doesn't work. And I realized it's because of the shading. It's because it's not all in one color. When they draw it in the textbook, when they draw a plane in the textbook, I guess I'll try and do it over this one. They'll have like, these parts are darker, and then they start spacing things out more. Like if you took like a magnifying glass to the page, you would see the way the inkjet printer worked was it just started making the colors more faded by spreading out the distance between the dots that it sprayed onto the page. And that gives it some three-dimensionality. Of course, those of you who are good with your art probably already knew this, but it's only been like a year since I actually learned about the importance of shading while trying to do pixel art, so cut me some slack. I wasn't really much of an art person before. The closest I've been to art is drawing diagrams for physics and occasionally math. And you're seeing how well that's working out. I mean, it's decent enough, I guess, but still leaves much to be desired. Anyway, what do we have next? For the following exercises, find the equation of the sphere in standard form that satisfies the given conditions. Are there any... Okay, I see the vector problems on the next page. But yeah, let's talk about the equation of a sphere, why don't we? So if the equation of a circle is... If the equation of a circle is x minus h squared plus y minus k squared equals r squared, this is a circle in the xy plane, then what do you think the equation of a sphere would be? What would be your educated guess? Think back to how the Pythagorean theorem extends from 2 dimensions to 3. Following that same pattern, you would correctly guess that x minus h squared plus y minus k squared plus z minus l squared equals r squared is the equation of a sphere in 3D space. If you just leave one of these terms out, what we get instead is a cylinder. So it's important to have all 3 terms because that way you add the additional restriction that, confines these points to not stray and not, go infinitely in a given direction. So that's the equation of a sphere. Let me see. So they give us, one of them has a center of -174 and radius 4. Another one has a center of -472 and radius 6. And then for another one, they give us diameter. And the diameter is PQ, where P is -157 and Q is -529. I think that might be an interesting one. And the next one is also a diameter. Actually, yeah, let's pick one of those diameter questions because it involves an extra step. We don't want to make it too trivial. The more steps are involved, the more we can learn. Okay, diameter PQ. So we have a circle with diameter, or not a circle, a sphere with diameter PQ, where P is -157, 7, and Q is is it? Negative 529. Negative 529. All right, so what makes this problem more interesting is that we need to know not only the equation of a sphere, but we also need to know the distance and midpoint formulas. Actually, yeah, we need both the distance and midpoint formulas. So you might have not used the midpoint formula for a long time. If you've been through Calculus 1 and 2, you haven't really had to use it, but it should be intuitive enough that you'll remember it as soon as you see this. Midpoint formula, you just take each coordinate, add their values, and divide by 2. You're just averaging them out. So midpoint, I'll call it C, point C. We'll call it x0, y0, z0. I guess we could have also called it hk and l, which I guess would have been more proper, is equal to negative 1 plus negative 5 over 2, comma, 5 plus 2 over 2, comma, 7 plus 9 over 2. 7 plus 9 over 2. And that would be, let's see, negative 6 over 2 is negative 3. 7 over 2 is 3.5, or 7 halves, depending on how you want to write it. And then 7 plus 9 is 16 over 2 would be 8. So this is going to be the center of our sphere. Now for distance. Do we remember the distance formula? So radius is going to be equal to the distance from the center to a point on the surface of our sphere. We've got 2 different points on the surface of our sphere that we can choose from. It doesn't matter which one we choose. And then what was the distance formula? In 2D, it was basically the Pythagorean theorem. It was distance equals the square root of x2 minus x1 squared plus y2 minus y1 squared. And this came from the Pythagorean theorem because if we draw 2 random points, here's x1, here's x2, here's y1, here's y2. X2 minus x1 is equal to this distance right here. Let me actually draw that in a different color. Let's do it in pink. This is x2 minus x1, x2 minus x1, and this is y2 minus y1. And if we're trying to find this, if this is our distance, then I think you can see the right triangle there and apply Pythagorean theorem. It's the same exact thing in 3 dimensions. If you want to find the distance between 2 points, then there's going to be a change in x and a change in y and a change in z, which all add up together to make the hypotenuse of a right triangle in 3D space. It will just be the same as the distance formula in 2D, but with 1 term added. So radius Or actually, we don't need radius, do we? We need radius squared, so I won't square root at the end, but let's write out the formula. So x2 minus x1 squared plus y2 minus y1 squared. Or you could do y1 minus y2 squared. It doesn't matter which one is subtracted from which, because if you're squaring it, it's going to come out positive either way. If you reverse the order of subtraction, you don't change the actual value, you don't change the magnitude rather, but you only change the sign, and the sign isn't going to matter because you're squaring it anyway. Still, in keeping with, patterns that you've learned from other formulas from analytic geometry, especially the slope formula, doing the second minus the first is probably just easier to remember since you have so many other formulas where you do second minus first, especially in physics. Remember all of those deltas, if you've done any physics at all? All of those deltas are usually defined as the final minus the initial, the second minus the first, the next minus the previous, however you want to word it. Anyway, I want to do, again, order doesn't matter, but let's do from center to Q, for example. That would be -5 minus -3, then 2 minus 3.5, and 9 minus 8. All right, we get r squared is equal to -5 minus -3 is -2, and then squared is 4. Two minus 3.5 is -1.5. -1.5 squared is 2.25. If you know that the square of 15 is 225, that's your shortcut for figuring this one out without a calculator. I mean, if you need the calculator, then fine, but it saves you a couple of seconds and a couple of button presses, so why not? Why not try to learn some of your higher perfect squares? 9 minus 8, that's just 1, and 1 squared was 1. I think I already said that, but just in case I didn't. And 4 plus 1 plus 2.25, 5, 7.25. Okay, and with that we can now write the equation of this circle. So the equation would have to be, or not circle, sphere. So the equation would have to be x minus -3, so x plus 3 squared, plus y minus 3.5 squared, plus z minus 8 squared, equals 7.25. That would be the equation of our sphere. All right, what do we have next? For the following exercises, find the center and radius of the sphere with an equation in general form that is given. Oh boy. Okay, fine. I mean, we might as well learn these skills. We might as well review. I'll do one of them. Which one do I want? So one of them gives us, wait, what? P 1, 2, 3. And then x squared plus y squared plus z squared minus 4z plus 3 is equal to 0. What? I don't understand. The other one... So one of them is giving you a point. I guess that's a point on the sphere? Oh, okay, I think I see what they're trying to get at. Actually, no, why are they giving us that point? They're giving us a point, and then they're giving us an equation of the sphere in general form. But the equation of the sphere in general form is all you need. You should be able to rewrite it in such a way that you get the radius and the center. So I don't know why they're giving us a point there. I might look at it later, but for now I'll just leave it alone in case there's some sort of twist that I'm not seeing at the moment. Let's take a look at the other one because it actually lets us complete the square more often. We've actually got 3 squares to complete. So it says we have the equation of a sphere is x squared plus y squared plus z squared minus 6x plus 8y minus 10z plus 25 is equal to 0. What can we do with this? So group the x terms, group the y terms, group the z terms, and move all the other junk over to the right-hand side of the equation. So I'm going to do x squared minus 6x I'll put it in parentheses for now, just to kind of organize it a little bit better, just for visual organization's sake. Plus y squared plus 8y plus z squared minus 10z equals negative 25 is how I will rewrite it. And now to complete the square, so I want to take half of 6 squared would be 9. Half of 6 is 3, and then 3 squared is 9. So x squared minus 6x can be related to, let's see, if I did x minus 3 squared, that would be x squared minus 6x plus 9. So yeah, if I add 9 here and I add 9 here, if I add 9 to this and I add 9 to this, then this becomes x squared minus 6x plus 9, which we can simplify to x minus 3 squared. Okay, similarly, I can do, let's see, 8y, that would come from so a plus 8 would come from a plus 4 if I did y plus 4 squared, that would be y squared plus 8y plus 16. So if I add a 16 here and I add a 16 here, then now I can rewrite this as just y plus 4 quantity squared. And then similarly for z squared minus 10z, so that minus 10 is coming from a minus 5 after squaring, after foiling. So z minus 5 squared is going to be z squared minus 10z plus 25. So if I add 25 here, and I add 25 here, I'm just going to add it to the minus 25 that we already have to cancel out. And there we go. And I'm left with 9 plus 16, which is 25. And that's nice. That means that r squared is 25, which means r is a nice and clean 5. I was expecting some sort of weird radical that we couldn't simplify for the radius, but I'll take it. I'll take an integer value radius any day. It's just more pleasant to look at. So yeah, I guess where do I want to write this? I don't want to do it on the next page. I guess we'll do it right here. So our equation can simplify to x minus 3 squared plus y plus 4 squared plus z minus 5 squared equals 25, or 5 squared if you will. So radius is 5 and center is 3 comma negative 4 comma positive 5. Center is 3 negative 4 5. And there we have it. Equation of a sphere from general form to, I've forgotten what the name was for this, standard form, right? I'm pretty sure. I mean, as long as you understand the idea, remembering the name isn't the most important thing, although it can help with communicating, so I should probably go back and look up the official terms for all the different forms. Okay, next up we have, for the following exercises, express vector PQ with the initial point at P and terminal point at Q. Okay, so we did this last time, except we did it for two-dimensional vectors, and this time they want it for three-dimensional vectors. So it's not really that hard to do. You just subtract, and we'll do one of them. I don't think we need to waste your time on... Actually, let me read some of the later ones, because I want to find... If we have a later one that has us doing that as a step anyway, then we might as well, do a problem that has more to it than just finding a single vector between 2 points. Let's see. Okay, I guess that might be a little bit of a twist. Okay, we'll do the third one, which says we've got a point P, -2, 5, -8. And we have a point M, which is 1, -7, 4. 1, -7, 4. And we want to find, again, the vector pointing from P to Q, the displacement between P and Q. That is... There we go. I don't know why my arrow ended up slanting down like that. So we're trying to find the vector with initial point P and terminal point Q, and M is midpoint of P and Q. M is the midpoint of P and Q. According to the problem. There are two ways you can do this. One way is to just use the midpoint formula in reverse to figure out where the point Q is, and then just do the standard thing to find a displacement vector between 2 points. The other option is to find the displacement between P and the midpoint and simply multiply that by 2, which is what I would rather do, but let's try both. Let's try both just for the sake of getting that mental exercise. So I'm going to first try the one that I consider to be easier, which is find PM. Find the vector PM, the displacement between P and M. That's just going to be a vector with components terminal minus initial, so 1 minus negative 2. I don't know why I have that outer layer of parentheses. I didn't need it. And then negative 7 minus 5. And then 4 minus negative 8. 4 minus negative 8. Okay, 1 minus negative 2, that's 3. Negative 7 minus 5, that's negative 12. And 4 minus negative 8, that's positive 12. Okay, and then PQ is simply 2 times PM is equal to 2 times 3, negative 12, 12 would be 6, negative 24, whoops, 24, not 25, and then positive 24. Okay, so that's one route we can take. Another route we can take is figuring out where the point Q even is, so that's not actually going to be too bad. It'll be, let Q be, I guess we'll call it x2, comma, y2, comma, z2. And we can say the midpoint, 1, comma, negative 7, comma 4. We can say 1, comma, negative 7, comma 4 is simply equal to negative 2 plus x2 over 2, comma, 5 plus negative, or no, wait. I'm looking at the point M for some reason I shouldn't be. 5 plus y2 over 2, and then negative 8 plus z2 over 2. Almost had a mental malfunction there. Not good. But the important thing is to stop and pause and catch yourself when you feel like you're about to make a mistake. And even when you're in the habit of doing that, still double check your work. Negative 2 plus x2 over 2 is equal to 1. So really, I could just multiply the 2 over here and end up with 2 negative 14 and 8 is equal to negative 2 plus x. Whoops. What did I do? Negative 2 plus x2, comma 5 plus y2. Yeah, the first path I took was definitely the easier path, and then negative 8 plus z2, and then negative 2 plus x2 equals 2. That means x2 must be 0. So x2 must be 0. 5 plus y2 equals negative 14. So that would mean y2 is negative 19. 5 plus negative 19 is equal to negative 14. So that's negative 19. And then z2, we've got negative 8 plus z2 is equal to 8. So z2 must be 16. Negative 8 plus 16 gives me 8. Okay, and now we have another step, which is figuring out the changes in x, y, and z between p and q. So p, q is equal to, I can't believe this one problem ended up taking up pretty much a whole page. Just goes to show you that when you realize there's an easy route, you should just take it. But doing it just once, doing it the hard way just once to show that the hard way does work is not bad when you're first trying to learn a concept. Maybe don't waste time on it when reviewing for an exam, but when you're first introducing yourself to the ideas, it can help to tackle it from multiple angles when possible. So let's see, we have 0, negative 19, and 16. So I want to do 0 minus negative 2, 0 minus negative 2, comma, negative 19 minus 5, and 16 minus negative 8. 16 minus negative 8. Oh, wait, and that's a vector, so I should be using angle brackets. There we go, not parentheses. So that's going to be 0 minus negative 2 is 2. Wait, something is wrong. I'll worry about it in a minute. And then negative 24. And then positive 24. Well, I know I've done something right because I got the negative 24 and the positive 24, but the 2 and the 6 disagree. What happened there? Let's see. 1 minus negative 2 is indeed 3. Negative 7 minus 5, that is negative 12. And then 4 minus negative 8, that is indeed positive 12. 3, negative 12, 12. Okay, so the 3 is right. So what went wrong over here then? Let's see. Negative 2 plus x is equal to 2. Hold on. negative 7, and 4. So 1 is equal to negative 2 plus x2 over 2. That would then mean that x2 has to be 4. Okay, x2 has to be 4, not 0. And then 4 minus negative 2 is equal to 6. Okay, that fixes it. There you go. I was just talking about double checking and looking out for mistakes. I couldn't have scripted this better if I wanted to. All right. Next up we have... It says for these next two, find the terminal point Q of the given vector PQ. If you know the initial point, that's probably an easy enough exercise. I will leave it alone. Next set of exercises says for the following exercises, use the given vectors A and B to find and express the vectors A plus B, 4A, and negative 5a plus 3b in component form. I think I'll do just the negative 5a plus 3b, since that's the hardest one. Negative 5a plus 3b equals what in component form for the following? I'll pick two of them. I'll pick the second one and the fourth one. So the second one says A is 3, and then negative 2 and 4. Negative 2 and 4. And then B is negative 5, 6, negative 9. B equals negative 5, 6, negative 9. Okay, negative 5a plus 3b would simply be negative 5 times this stuff. It just distributes. And then plus 3b. So plus 3 of negative 5, 6, negative 9. Whoops. Angle brackets, not parentheses. Equals, let's see, negative 15 plus negative 15, that's negative 30, comma, negative 5 times negative 2 is 10, plus 3 times 6, 18, with the 10, that's 28, and then negative 5 times 4 is negative 20, and plus 3 times negative 9. 3 times negative 9 is negative 27. With the negative 20, that's negative 47. Negative 47, and I did not make enough space for this. Okay, let's try writing that better down here. Equals negative 30, comma, 28, comma, negative 47, close with angle brackets. There we go. That looks much better. Okay, that's one of them. And then the other one isn't going to be too bad. I'm actually just going to do half of it and leave the other half to you. So they have, the only reason I'm including it is because they've written A and B in terms of standard basis vectors, or standard unit vectors. So they have, they have A equals I plus j plus k, I hat plus j hat plus k hat, and vector B is written as 2i minus 3j plus 2k. 2i hat plus minus 3j hat plus 2k hat. So you can just rewrite them in component form. You can rewrite the A as 1, 1, 1. And you can rewrite the B as 2, negative 3, 2. 2, negative 3, 2. It's just like what we did last week, except last week we didn't have this k hat thing, so now you've been formally introduced to it. K hat is the vector of magnitude 1 in the positive z direction. K hat, in textbooks they just write a bold K, but I can't really write in bold here, so that's why I use the hat symbol to identify it as a vector, but also to identify it as a unit vector specifically. So k hat is 0, 0, 1. It's a vector of magnitude 1 in the positive z direction. Multiply it by any number and you now have a new vector in the z direction whose magnitude is whatever you multiplied by. Okay, and the rest plays out the same as before. Multiply these by negative 5, multiply these by 3, combine them and get some sort of resulting vector from them. You've seen how that's done, so I won't bother with it. Let's move on to something else. For the following exercises, vectors u and v are given. Find the magnitudes of vectors u minus v and negative 2u. Finding magnitudes of vectors in 3D pretty much just does the same thing as in 2D. We mentioned last time when deriving the Pythagorean theorem for 3D space that it can be used to find the magnitude of a 3D vector. You just square each of its components and take the square root. It's just Pythagorean theorem in 3D all over again. Must be nice seeing that so many of the formulas you were using in 2D still work pretty much the same in 3D. Less stuff to commit to memory, I suppose. So let me go ahead and pick a couple of these. Let's do the first and the third. So it says find the magnitudes of u minus v and negative 2u. I'll just do u minus v. Find the magnitude of u minus v. for these two scenarios. Scenario 1, you have u equals 2i plus 3j plus 4k, 2i hat plus 3j hat plus 4k hat. And then v is negative I plus 5j minus k. Negative I hat plus 5j hat minus k hat. Oh, hey, is it pronounced Sharknado Fredo? I'm not sure what WSP stands for, but welcome. I've just been doing some basic vector stuff in preparation to review multivariable calculus, but if you have any questions, math, chemistry, or physics, you can post them in the chat. We don't have that much time left on the clock, but you can post your question and we'll see how far we can get into answering it. And if you're just along for the ride, then enjoy, I guess. Anyway, I'll just continue with this problem and I'll look again and see if you have any questions posted once I'm done with it. So, where were we? Right, I wrote down vectors u and v, so I guess now we need to find u minus v. Actually, no, before that, I want to write out the other scenario, so that's scenario 1, and then scenario 2 gives us u equals 2 cosine of t comma negative 2 sine of t comma 3. And then v is just a simple 0, 0, 3. V is just 0, comma 0, comma 3. And they say where t is a real number, which is something I would have naturally assumed anyway, but it's good that they mention it just, for good measure. Anyway, let's find u minus v first for each of these. So for the first one, I actually want to rewrite u and v in component form like this because that's what I'm comfortable with. So u is going to be 2, 3, 4, 2, 3, 4. And then v is going to be negative 1, 5, negative 1. Okay, and then u minus v. Let's switch colors again. U minus v is going to be 2 minus negative 1 comma 3 minus 5 comma 4 minus negative 1. And that gives me 3, negative 2, and 5. It looks like 3, negative 2, and 5. We'll calculate the magnitude for it in a minute. Let's do the same for the second one. So let's find u minus v. For this second set, we've got... Oh, well, if we're just subtracting 0 for those first two terms, then that's easy. Just copy them over. 2 cosine t minus 0 is 2 cosine t. I'll skip on writing the subtraction step like I did before, since this one is trivial. And then negative 2 sine of t minus 0 is negative 2 sine of t. And 3 minus 3 is 0. All right. Magnitude of u minus v. Just apply the Pythagorean theorem in 3 dimensions, as I mentioned a couple minutes ago. For this one, magnitude of u minus v will simply be square root of 3 squared plus negative 2 squared plus 5 squared. Is that going to be a nice number that we can actually take the square root of? 9 plus 4 is 13, plus 25 is going to be 38. No, that's not going to simplify. Is equal to the square root of 38. And if I factor it, 2 and 19, yeah, those are prime numbers, so I can't pull anything out of the square root either. So there's the magnitude of that first one. This second one might impress those of you who haven't worked with the Pythagorean identity in a while. Although I doubt that's many of you, because if you've been doing calculus 1 and 2, then you've used the Pythagorean identity many, many times by this point. So we're going to have magnitude of u minus v in this case is just going to be the square root of 2 cosine of t squared plus negative 2 sine of t squared plus, well, 0 squared. Okay, so that's going to be 4 cosine squared. That's going to be 4 sine squared. 4 cosine squared of t plus 4 sine squared of t. We can factor out the 4. And if you know your trig identities, then you know that cosine squared of t plus sine squared of t is always equal to 1. So this reduces to the square root of 4 times 1, which is the square root of 4, which is 2. At least that one turned out to be a nice number. All right. I think we have time for one more before I have to wrap things up for the day. Or maybe two, depending on how simple they are. Let me see what else we have in this book. The next set says, for the following exercises, find the unit vector in the direction of the given vector A and express it using standard unit vectors. Oh boy, I think this one is actually going to take up all of our remaining time. There are multiple steps here after all. I guess that's true of most math problems, but you know what I mean. More steps than usual. Which one do I want to pick? Oh God, do I dare do 95? Nah, let's... Yeah, those, I mean, yes, it has multiple steps, but it's stuff that we've already done. I don't think we need to rehash that. Yeah, let's just do 92, which says vector A is 4, negative 3, 6. 4, comma, negative 3, comma 6. So we have a vector A with components 4, negative 3, and 6. And our job is to find a unit vector in the direction of A and express it using standard unit vectors. Okay, the unit vector for A is just going to be A itself divided by its own magnitude, as we showed last time. Last time we did it for 2D vectors, this time we're going to do it for 3D. But the steps are essentially the same, so it's going to be 4, negative 3, 6 over, the magnitude is going to be the square root of 4 squared plus negative 3 squared plus 6 squared. Let's see, 4 squared is 16. And then that's going to be 9, so 16 and 9, that's 25. And then 6 squared is 36. 25 and 36 would be 61, which is a prime number, so that's not going to simplify. So 1 over the square root of 61, essentially times 4, negative 3, 6 is equal to 4 over root 61, comma, negative 3 over root of 61, comma, 6 over root of 61. And they wanted this in terms of standard unit vectors, so we're going to write it as 4 over root 61 I hat plus, or I guess this would be minus, actually, minus (3) over root 61 j hat, and then plus 6 over root 61 k hat. Okay, that actually didn't take as long as I thought it would, so maybe we can squeeze in one more. Let's see what else we have on offer. Determine whether the vectors a, b, and p, q are equivalent vectors. That might be interesting. I mean, essentially you're just calculating two vectors and seeing if their components are the same. It doesn't matter that they start and end at different points as long as they move the same distances in x, y, and z. So yeah, I think we'll skip those. What about this set? It says, for the following exercises, find vector u with a magnitude that is given and satisfies the given conditions. We did something like this last time for two-dimensional vectors. I don't think there's anything new to show with a 3D version of it. You just get the unit vector and multiply by whatever desired magnitude you want. Pretty much what we did here, and then multiply. If they wanted it to have a magnitude of 7, you multiply it by 7, and so on and so forth. Yeah, nothing new there. Determine a vector of magnitude 5 in the direction of vector AB. Okay, so pretty much the same, but with extra steps. And that one's also the same. What about this one? Consider the points A, which is 2, alpha, 0, B, which is 0, 1, beta, and C, which is 1, 1, beta, where alpha and beta are negative real numbers. Find alpha and beta such that the displacement from O to A minus displacement from O to B plus displacement from O to C equals, or the magnitude of that combination of displacements equals the magnitude of the displacement from O to B. Oh goodness, I don't think that's a good problem to end on, so pass. Maybe next week. And that one is similar. Yeah, I'll look at these on my own and see if they're worthwhile, if they present any interesting ideas, and if they do, then I'll be sure to cover at least one of them next week. Next one says, let P, x comma y comma z be a point situated at an equal distance from points A, which is 1, negative 1, 0, and B, which is negative 1, 2, 1. Show that point P lies on the plane of equation negative 2x plus 3y plus z equals 2. I think that one might also involve more steps than we have time for. Do we have anything quick that we can do? Anything at all? I'm trying to look through these and find something, but I'm coming up with nothing. Points A, B, and C are collinear in this order if the relation... Yeah, all of these seem to be proof problems now, and I don't think we have time for an involved proof. Okay, I guess I'll just go back and wrap up with one more of these. Find the unit vector problems. Okay, how about this one? So it says we've got V equals 2, 4, 1. V equals 2, 4, 1. And we want a vector u such that its magnitude is 15 and has a direction identical to v, same direction as v. And I can hear it raining outside again. Nice, nice. Okay, so we want a magnitude of 15. Okay, easy enough to do. Just find the unit vector first. So we'll do v over its own magnitude, and that will be 2, 4, 1 over the square root of 2 squared plus 4 squared plus 1 squared. Let's see, that's going to be 1 over the square root of, 4 and 16 is 20, and then plus 1, that's 21. So 1 over the square root of 21. Okay, and then this will be the same unit vector as u. If two vectors have the same direction, then their unit vectors are identical, so you could say that this is equal to u over magnitude of u. Therefore, u would just be, if we multiply both sides of this by the magnitude of u, which is 15, then u would just be 15 over square root of 21 times 2, 4, and 1. Like so. And distribute and simplify where we can. 15 and 2, that's going to be 30 over root 21. 15 and 4, that's 60 over the square root of 21. And just 15 over the square root of 21. Okay, so I tried to make it a little bit different from what I did last week with the two-dimensional version of this problem. Adding in that whole equals the unit vector of u. That's a step that I didn't take last time. It's just another perspective that you can have with this sort of problem. But yeah, I guess this is where we will have to end it because I can't find another problem that's quick enough to fit into just a couple minutes. So yeah, that'll be it. If you have questions for other topics that you want to look at, then feel free to come join next week and post your questions. Otherwise, I'm just going to continue with this stuff next time. We'll do a little bit more with these 3D vectors, and we'll start looking at some operations that can be done with vectors other than simple calculate the magnitude or multiply by a scalar. We'll look at the dot product and maybe even the cross product if we get through dot product fast enough. And yeah, I guess that'll be it. So hopefully this has been helpful, and I will see you in the next one.